Um, Don't write this down. Is this going to spontaneously happen, this process right here, at negative 10 degrees Celsius? No, not going to happen, right? Will that happen then? Spontaneously, on its own. Right. Will the reverse happen at that temperature? It will not. You see what I'm saying about an irreversible process? So when we're talking about entropy, we're referring to spontaneous, happening on its own without any outside input, irreversible processes. That process is going to occur at 10 degrees Celsius. Okay? The reverse process is not going to happen. That would be cool, but it's not. All right. Save a lot of energy for us, wouldn't it? Moving on. So it's hard, it's difficult, in fact, really impossible, to measure the entropy of a substance, just the straight up entropy. Okay? So what we do is we end up measuring the change in entropy, or calculating the change in entropy, and which is the whole delta S thing. So as we were saying earlier, the delta S equals Q reversible over T at constant temperature, where the delta S equals change in entropy. We've already defined all these, I'll do it again. Q equals the heat of a reversible process. The book goes into why we consider that. And T is the absolute temperature. So once again, delta S is change in entropy. Q is the heat of a reversible process. T is the absolute temperature. It is a state function, just like we've talked about some other state functions, meaning it's independent of the pathway. And the units, and this is important, because this is a place where you guys will mess things up on occasion. Okay. The units for entropy are joules per Kelvin. What have our other energies been in so far? Kilojoules. Kilojoules. Our other units have been kilojoules. Okay? You'll see this here in a little bit, but our enthalpies are in kilojoules. You're going to find out our Gibbs free energies are in kilojoules. The delta S's, or the entropies, are in joules. They're very, very small. So to have numbers that are fairly easy to speak about, 10, 20, 55, whatever, we will, they'll be in joules. Otherwise, it's going to be 0.005 and all that kind of stuff. All right, moving on. If the temperature of the system and surroundings is equal, then the sum of the change in entropy for each component will be 0. However, a real process, one that actually exists, one that actually happens, is irreversible, so the total entropy has to be greater than 0, which leads to this equation. And all of this is greater than 0. What that is essentially saying is the entropy of the universe is increasing. There's a little analogy, a couple phrases that kind of go along with this. Remember, we talked about the first law of thermodynamics earlier. Essentially, the little phrase that goes with the first law of thermodynamics is you can't win, you can only break even. I mean, you can't create or destroy energy, right? You can't win, you can only break even. The second law of thermodynamics says you can't break even. So what are we left with? We lose. Remember, first law says you can't win, you can only break even. Second law says you can't break even. Only leaves one other option. We lose. Okay, so we and the universe is losing. That's all right. It's fun to think about. So anyway, there's an interplay here between the system and the surroundings. Okay? If the entropy, and I know we don't know what entropy is yet, we'll get to that. But if the entropy of the system increases, then this is going to have to decrease, and vice versa. So there's an interplay back and forth, because the entropy of the universe will always be greater than 0. All right, so what is entropy? Well, it says down there at the very bottom at the very bottom in a bullet point. Essentially, it comes down to this. It's the spreading out or dispersal. Now, you have all probably learned, if you've had any information on entropy at all, it's like the particles are getting spread out, or disordered. You guys have probably heard things of disorder. Well, we're trying not to think of disorder anymore because there's other things that go into that. But the best thing to think about is the spreading out of energy. So it's the dispersal of energy that we're looking at. Now, you guys probably, those of you that have had a little bit of the thermodynamic stuff, have probably had the analogy about your bedroom or something like that. You guys have that analogy, or maybe your book bag or your locker or something like that, right? So, no, your room's probably fairly neat and organized. Yeah, I'm starting to figure you out. Katie, how the feeling that your bedroom is not incredibly organized and neat right now? Would that be true?
Yeah, I clean it every week.
Do you really?
It gets like dirty right after.
Okay, you mean like stuff just all over the place, right? So, how does it get clean?
Stuff up.
Yeah, you do that. Does it spontaneously happen? Like if you go home today, is it all going to be neat and organized and picked up? No. It's probably currently not in that shape, right?
I cleaned it last night.
Oh. Then it probably is, right? Next Monday, is it going to be nice and clean and organized? Probably not. Now, so its tendency is to have everything spread out, right? Now, think in terms of energy. How do things get spread out? Kind of spontaneously happens. You just walk in and just throw things on the floor or whatever, right? Most of you probably do that to some extent, except for Grace. Okay? So it takes energy to put things away. You put things where they belong, right? Otherwise, they just naturally just kind of fall apart. That's what I'm trying. Even though there's particles that we're talking about are being also spread out, there's energy also being spread out, is where I'm going with that. So you can think of either matter or energy. All right. What do we, okay, flipping it over, we need a molecular interpretation of that. So a particulate interpretation of that. There are 3 main types of molecular motion we're going to look at. There's translational, there's vibrational, and rotational. Okay? All translational means is a particle moving from one place to another. So thinking of a gas, it would be an oxygen molecule moving from here to here. That would be one way. Now that's what you all think of, I think, when you're thinking of molecular motion. Particles moving from one point to another point. Is that fairly accurate? Okay. You can also have vibrational motion. Okay, and I think you guys are also familiar with that. The particles that make up this desk, the atoms or molecules that make up this desk, are those molecules or atoms moving from one place to another in the desk? No, they can't. They're locked into place. However, since they have some heat, since they have some energy, what those particles are doing is they're vibrating, okay, from side to side. That makes sense. You guys are probably familiar with that idea, right? And the last thing, but there's a couple of different ways molecules can vibrate. Not just the entire molecule itself, but let's look at an oxygen molecule. A water molecule. There's other sorts of vibration it could have. Yes, the entire molecule itself could be changing positions. However, within the molecule, there can be some vibration within the bond, meaning there can be some shortening and lengthening of the bond to some extent. The other thing that can happen is there can be changes in that bond angle. The molecule can bend back and forth a little bit. So there's more types of, there's intramolecular vibrations, meaning molecules are moving relative to each other. There's also intermolecular vibrations, where there's vibrations occurring within the molecule. And then lastly, there's also rotational motion. Once again, that could be either the entire molecule itself rotating on an axis, or it could be, let's look at methanol. Okay, this whole methyl group here could be rotating. And I can probably do that a little bit better with this. What do I want to do there? Yeah, I'll just do that. Doesn't matter. Okay, where this would be the oxygen atom, over here would be the hydrogen, and then here's the little carbon with the 3 hydrogens around it. Okay, so not only could the whole molecule rotate, but that component right there could rotate also. Where I'm going with this is there is and then as this is rotating, these could be bouncing back and forth this way, or the bonds could be shortening and lengthening. Do you see all the different types of energy that could be going on in this molecule? Simple molecule. Okay, and then the molecule itself could be moving from here to here, the translational piece. Where I'm going with this is there's a huge amount of different types of motion that could be going on in a very, very simple molecule. And what entropy does is kind of accounts for all of those things. Now, you can imagine if we had a mole of this stuff, methanol, ethyl alcohol, okay, which would be about, what would that be? 32 grams of the stuff, which isn't very much. Okay, we're talking around 30 milliliters of this. 6.022 times 10 to the 23rd of these things, with all the associated different particles. That's a huge number of different types of motion going on, right? Anyway, all of those are considered when we're examining, when we're considering all this. We're looking at all the positions and energy that molecules can occupy in the system. This single set of positions and associated kinetic energies is known as a microstate. So, imagine you guys are doing this, you guys do this, take those pictures now where you just press the button and it goes, like the stop action photography, that kind of thing. Okay? You can imagine doing that with one of these molecules and all the different positions that could be occurring for all those atoms relative to each other. Each of those would represent a single microstate. And then you multiply that by the mole of these things that we have. I mean, it's just this infinite number of possible positions that all these molecules could have relative to each other. I mean, it's just mind-boggling. Well, there's this guy back, and again, it was around the Civil War time, his name was Boltzmann. You guys may have heard this guy name before. He's the guy that came up with this equation that related this entropy to these ideas of microstates. That equation that I wrote there, S equals K ln W. Ln refers to natural log, okay? As you can, the S is the entropy like we talked about. The K is Boltzmann's constant. I'll go ahead and give you a value for it, but I'll tell you here in a little bit, we're not ever going to use this equation. It's unfortunate, but we won't. S is entropy, K is Boltzmann's constant. The value is 1.38 times 10 to the negative 23rd joules per Kelvin. And then W represents the number of microstates. That equation right there is probably one of the most famous equations of all equations that exist. I know you guys think it's equals mc squared, and that was cool, but that equation right there is a much more important equation there as far as what goes on in the physics and chemistry worlds. I'm not going to go into that. You can read about it in the book. Okay, here's where I'm going with this though. Any increase in the number of microstates is influenced by temperature, volume, and the number of particles. So, the entropy of the system may decrease, but there's going to be then, we already talked about this, a corresponding increase in the entropy of the surroundings. Mainly because, like we said, it's equivalent to the entropy of the universe. Therefore, looking at the entropy of a system, it's generally going to increase for the following processes. And I'll write these up here. This is not mind-boggling. It makes a lot of sense. Anytime a solid or liquid becomes a gas, that will be an increase in entropy. These are all increases in entropy, meaning that there are more microstates available, more positions available. Anytime a solid becomes a liquid melting, or a solution becomes in solution, that also increases the number of possible microstates, the positions that each of those particles can be in. An increase in entropy. Or, and this is one that you guys, they'll throw in the AP a lot, an increase in number of gas particles. Would indicate an increase in the number of microstates, therefore an increase in entropy. That one actually catches, they'll throw that in an AP exam at least once, if not more times, within any one AP exam. I'll give you an example of this. Anyone have any idea what that might form? This is just more of a, just see if you guys know this kind of thing. Very common substance. If you don't know, it's okay. I would hope you would know. Does anybody know what NH3 is? Ammonia. What? Did you say that earlier? Okay, so that's ammonia. Is this balanced? How would it be balanced? Would you guys agree? Yeah, I'm with you on that. Okay. What happened? How many gas particles here? It's not hard. Go ahead and answer that question. 4. How many gas particles here? 2. How did the entropy change? What happened to the number of microstates? It decreased. We have fewer particles, therefore we can have fewer opportunities for them to be in different positions. Therefore the entropy decreased. Now let's go back to Katie's bedroom. Well, let's not actually go there. Let's go back to the analogy of Katie's bedroom. This is what Katie did last night. Would you agree? She took all these pieces that were randomly spread around and did what? Combined them and put them into little places where everything's together now. Okay? We're decreasing the number of microstates. Okay, moving on. Oh, here's a good question. 2 more examples. actually more examples than that. You guys know what that is?
Coal.
What?
So is carbon dioxide a solid? Is it
It's
just
that, I
solid?
forget what it's called, it's that stuff that.
There we go, dry ice. You guys are familiar with that, right? Or at least of the existence of it. I don't know if you've ever played with it, but familiar with it. What does dry ice do? It becomes a gas. What's that process called? Sublimation. Okay. Increase or decrease in entropy. Increase or decrease in the number of possible microstates. An increase. There's more positions available because it's filling more space. It's a gas now. Okay. So we have an increase in delta S. Here we have a decrease in delta S. Ooh. What's that? Table salt. What's going to happen if I put it in water? Going back to chapter 4 a little bit. What's it going to do? Okay, we can use the 9th grade word if we want. What's salt going to do when you put it in water? Dissolve. Now, what's the AP chemistry word that starts with the same letter? Dissociate. Very good. What's it going to dissociate into? Sodium ions and chloride ions. What happens to the entropy? What happened to the particles? They were clumped together before, now they're dispersed through a greater volume. More microstates, more positions for them to be in. Is that an increase in entropy or a decrease in entropy? It's an increase in entropy. Okay. Whoa, didn't put my S up. Let me give you 2 more examples. Which has greater What is O3, by the way? Ozone. Ozone is not the atmosphere.
O3 is toxic, O2 is not. Bond at.
What?
No, I thought the same thing.
The ozone was the atmosphere?
Isn't the atmosphere made up of ozone?
No, the atmosphere is made up mostly of nitrogen, about 78%, about 21% oxygen, and about 1% of 18 other things.
Okay.
Of which in the upper atmosphere, now this is good, in the upper atmosphere there is a small amount of ozone. What's the purpose of the ozone layer? Right, it absorbs UV radiation coming from the sun. Okay, anyway, so it's a very small amount. When it's closer to the ground, what do we call ozone? It's a component of something. If you ever lived in Los Angeles, you'd be well aware of it. Small, yeah. So it's something we don't want. Has anyone ever burned up an electric motor before? Seriously, it's possible some of you have had an electric motor burned up before. For example, over Thanksgiving, somebody was using one of those electric knives. You guys ever see those before? Yeah, the motor burned up in it. You ever smell an electric motor burned up? No? It smells like it produces ozone, so that's what it smells. Moving on. Ozone or oxygen, which has greater delta S, greater entropy? VO3, why?
Because there's more ways it can move.
Yeah, there's more particles. There's more positions for those particles to be in. There's 3 atoms instead of 2 atoms. Greater, so ozone has greater delta S. What about calcium or magnesium? Noah says magnesium. Anyone concur?
That's it.
Do you have any evidence behind that?
It's
50-50.
on the table, it's higher.
It's higher on the periodic table. Meaning what?
There's more.
Say this again?
There's more mass.
In what?
Wait, right? Yeah, easy.
And magnesium has a higher mass than calcium?
Oh, I was thinking of sodium. So calcium.
Calcium would have a greater entropy. Why? There's more stuff. There's more particles, more protons, more neutrons, more electrons, more positions for them to be in. Greater entropy, more microstates. Okay. Okay. Now we're going to actually start to learn how to calculate the entropy of a system in chemical reactions. We're going to use standard molar entropy. See the little subscript or superscript 0 there? That means, once again, standard conditions, which is 1 atmosphere pressure, 1 molar solutions, and for solid, it's how it exists as a solid. And at 25 degrees Celsius, sorry about that. As you can see, I said it's similar to delta H. Now, in your book, that means we're going to have to look up some standard molar entropies, okay? In your book, I think I don't even have a note on there. So we're looking at pages 860. There's a small chart on pages 860. If you could turn in the books right now to the A5 to A10 in the appendix, that's the other place that these are located, A5 to A10. Kaylin, you probably didn't remember to bring the book, right? Well, like I said, when you get around to it, but the sooner you do that, the more of those we'll have laying around. Okay, now, I told you we were going to look at this at some point today, so now's a good time. Looking at the titles of the columns here, obviously we see substance. The first thing we've already looked at are the delta H's, okay? Those delta H's are given in kilojoules per mole, just like we have been using all along. But the next one is, over on the far right side are your delta S's, or your entropy, sorry about that. And notice they are given in joules per mole. Here in a very short period of time, whether it's going to happen today or whether it happens tomorrow, there's going to be an equation that's going to relate delta G, delta S, and delta H together. We're going to add them all up. Obviously, we're going to have to make some conversions for our delta S's. We're going to have to convert those to kilojoules. That is a place that they'll catch you on the AP exam on that. But anyway, one thing I do want you to notice, in our delta H's, remember we did have substances that had enthalpies of 0, enthalpies of formation of 0. Those are the ones in which, at standard conditions, they already existed in that state. Oxygen gas was one. We looked at, what else was it we looked at? Nitrogen gas was one. You guys have run into that. Pure solids had an entropy of 0. I think there were some calculations we did where that was true. Here's the thing. At 25 degrees Celsius, there will never be an entropy of 0. Every substance is going to have, everything is going to have some sort of value for its entropy. Would anyone like to explain why that might be? What's that? They all have energy of some sort. Because if we're not at absolute 0, which, by the way, you can't get there, but since they all have energy, there's going to be motion, whether it's the electrons moving or the atoms within the molecule moving one way or the other, they're going to have some energy. Okay? There's going to be movement, therefore there's going to be some entropy there. Okay. Now, there is a condition under which you can have 0 entropy, and it says that right there, right under the bullet point. a pure crystalline solid at 0 Kelvin. Now, like I just got done saying, 0 Kelvin represents absolute zero, can't happen. But we have to have a reference point, and there's the reference point. So everything is going to have a temperature of some sort, therefore it's going to have an entropy. All right. As we were saying earlier, we already talked about that. The entropy generally increases with molar mass and molecular complexity, meaning more complex molecules are going to have a greater chance of having more microstates. Gases have greater entropy than liquids, which have therefore greater entropy than solids. We've already talked about that up here. And we can determine experimentally changing the entropy through phase change and calorimetric experiments. Moving on, let's look at our first example. You're going to want to have your books still open to that appendix, I think. First example is determine the change in entropy for the following chemical reaction. So we're going to say take some nitrogen monoxide, react it with oxygen to form 2 nitrogen dioxides. So what you guys are going to have to do is use that summation equation, find the enthalpies of formation, or sorry about that, the enthalpies, I lied, the entropies of each of those substances, multiply by the proper coefficients, and add them up. The equation, as you saw, was on the previous page. Did you guys see the entropy of the reaction? Which is exactly the same as the delta H reaction equation. It's exactly the same idea. But go ahead and take a moment to do that. We'll talk about the implications of your correct answer here in a bit. Just out of curiosity, does anyone have a value that they'd like to share?
146.6 joules.
Say this again?
146.6 joules.
Okay, with the values, when I did it, I used it, so the values out of a different textbook. This is obviously, you pulled your values from another one. Negative 146 is what you guys got? Then that must be right. In the old textbook, it was negative 145.34, but it doesn't matter. That's cool. It's close enough. Okay? So anyway, you said negative 146.6. What's the unit? Very good. Joules per mole Kelvin. Okay. All right, moving on. What does that mean? What information does that provide? What happened to the entropy? It decreased in entropy. What does that make sense with the reaction? Let me write the reaction up here. Could I have asked you qualitatively before we even did the calculation, what would be the change in entropy here? You guys would say that it decreased in entropy because we took 3 particles of gas and converted them into 2 particles. Katie cleaned up her room. Okay? Does this verify that? Yeah. So there we go. All I'm just trying to do is show you how the quantitative and the qualitative piece agree with each other. Okay. All right. This is it. How much time do I have? We are going to do thermodynamics in 45 minutes or less. It might be a record, but that's okay. Here's what's going to happen. I'm going to cover this. We're going to be done with it. Maybe not the chart at the bottom. We probably won't get through that because that's going to take some time to think through, okay? But I'm going to give you the information. When you guys start working on the assignment out of the book, very similar but in a bigger way, at first you're going to sit there and look at these questions and go, I don't even know what the question's asking. And it's going to be that way for a little while until you dive in. And then you're going to start bouncing ideas off of yourselves and off of me. We're going to have conversations. And you're going to say, oh, I start to get it. And so at first it's going to seem like it's really, really hard. And then all of a sudden it's all going to start making sense. At the AP level, it's all going to start making sense. You're going to go, oh my gosh, this is easy. And that's going to be cool. And that's going to take you through until you take physical chemistry in college. At which point you'll go, I have absolutely no idea what's going on. Again. I'm just saying. Okay? So at some point in time, in the very near future, you're going to get this figured out as far as you know. So here we go. Lastly, Gibbs free energy. Delta G. A guy by the name of Willard Gibbs. Hey, our first American. Late 19th century, so we're talking 1800s, late 1800s here. Basically, what he was looking at was, hey, how much energy of these processes that we're looking at, these exothermic processes, how much of that energy, of all the energy that's there, is available to do useful work? Now, I do want to point this out to you once again. You don't have to write this down. I just want to remind you of this. Remember, the change in the internal energy, delta E, was equal to Q plus W. You guys remember that equation from, we're going to have a little quiz over some of that stuff tomorrow, right? Okay. Q plus W. Q is obviously heat, okay? W is work. Every process is going to have a change in energy of some sort. How much of that energy is available to have work done is what we're looking, that's what Gibbs is trying to find out, okay? Anyway, moving on. As you can see, there's an equation there. I told you guys earlier that this was going to be, we're going to combine all these things together, and there it is. That is a huge, huge equation for us. Delta G of the system. Now, you won't have to write system from now on because it's understood that we're referring to the system, okay? But the delta G is equal to the delta H plus negative T delta S, blah, 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 blah. Obviously, instead of saying plus negative T delta S, it's just a lot easier to write. Delta G equals delta H plus, or sorry about that. I did it anyway. Negative T delta S. Get rid of that plus sign on that second equation. I can't believe I did that. That's weird, wasn't it? Let me change that. Did you get rid of the plus sign? So, delta G equals delta H negative T delta S. Also, very similar to the delta H's and the delta H's, or the delta S's, we can have use that summation thing so we have products minus reactants. So the delta G of formation of the products minus the sum of the delta G of the formation of the reactants. Here is the thing, and I'm gonna relate that to something that we have already done recently. And then provide a summary for you. First bullet point. If delta G is less than 0, so what sign is it going to have? It's going to have a negative sign. Delta G is negative. Okay, there's another way of thinking of that. The reaction or process, whatever you want to call it, is thermodynamically, this will be the last time I write this for a little while. Now, what does thermodynamically favored mean? Spontaneous. It's going to happen in the direction that it's written all on its own. And that's the key. The reaction is thermodynamically favored was spontaneous in the direction that the process is written. That's why I did that ice forming water thing earlier. Okay? Not obviously, if delta G is less than, or sorry about that, is greater than 0, the process is non-spontaneous or not thermodynamically favored in the direction written. What's that? We're going to get there. We actually don't know about that yet. That's a chapter that we're going to cover in March, but you'll get it when you get the concept. So here we go. Now, what is interesting though, it is spontaneous in the reverse direction. So obviously if it's non-spontaneous in one direction, it will be spontaneous in the reverse direction. You've already kind of talked a little bit about that earlier. And then lastly, as Noah just asked, if delta G is equal to 0, anyone want to take a stab? Okay, you guys have heard about chemical equilibrium? Or just equilibrium in general? Right. If delta G is equal to 0, that means the system is at equilibrium. The process isn't going to occur in either direction. Does that make any sense? To a little bit that you guys know about chemical equilibrium. Okay, now we are going to use that idea of a process being at equilibrium to help us solve for delta S later. Not this instant, but later. A couple things I want to point out here. First of all, the magnitude of delta G. Is shoot, I want to even say indicative, but I want to say that because that's dumb. What's the word I should related to? Is directly related to the extent of the process or reaction. Now, we don't know about this yet because we haven't covered the equilibrium chapter, but some reactions have a tendency to have the forward reaction be the dominant reaction. Meaning that it's going to, the more negative the delta G, the further the extent of the reaction. If that makes any sense. Now, we haven't started playing with any of these numbers yet to find out what is a large value of delta G, or, you know, a very negative value of delta G. But, I just do wanna make that comment. Let me see if there's anything else that we can play with here before we shut down for the day. Oh, well then, let's go ahead and do that. You'll see a bullet point down there, not too long after that. Thermodynamics doesn't say how fast the reaction is, that's governed by kinetics, okay? It tells us whether it could happen, not whether it's actually going to happen or not. And then finally, that last little place. We can find out the temperature at which a process becomes spontaneous or not if we say that, and it's already written there. You don't have to write it down, it's already on the pages. If delta G equals 0, we're at equilibrium. And if that's the case, delta G equals delta H minus T delta S. Okay, fine. Well, if this is 0, then do we not have delta H equals, sorry about that, how am I going to do that? Oh, it equals T delta S. And it shows it all right there, okay? And therefore, we can find out the temperature at which point a process will become spontaneous, which is pretty cool. And we'll practice some of that stuff. Obviously, that's going to be embedded in some of the problems I give you guys. Listen, that was a lot. It really was, okay? When you guys walk in here a lot of times right after lunch, it's kind of like what I used to be in French class in high school right after lunch, knock myself up against the wall and fall asleep. Okay, I get that. Right, Galen? Okay, I understand that. It kind of sucks to go into this class right after lunch, because you literally probably want to fall asleep. Okay? That was a lot of information, very heavy information. It will all make sense. If you try. If you try. Right, Colin? It's true. All right. Good job. Yes.
Just a quick question for you. Your options are